y, z. This is x or y. This is x or z. Y or, this is not z, correct? So this is y or not z. Y or z. So now, those are the sums, right? Now we need to do the product, which is an and. We get the answer out here. Okay. You guys, fairly straightforward? Now for the question that you asked. So how do we take this truth table and find sum of products? Okay. So you have x, y, and z. So somewhere along the way, there's going to be x, y, z plus x, y, z plus x, y, z plus x, y, z. But we're going to have different flavors, right? So let's take a look at this first row. What could give you that result from what you know? This is and, correct? 0 and 0 and 0. That's a straight and operation, right? So there's no big secret there with me. That was 8, correct? Although there are other things we might have to come back and revisit that. So this is an and. That's a 1. That's a 0. What could possibly make 0 and 0 and 1 equal 1? What could possibly do that? What now?
It's a 1.
Okay, but we're stuck with and. Who said what?
X, Y, or Z.
Okay, but we're stuck with and, right?
Yeah, X and Y or Z.
X prime,
not
Y
X
prime.
prime.
So you're saying we might need a complement, right? Okay, right. Give it to me again. X prime,
Y prime.
does that match up what we're getting in that second line? Would that work?
Yeah.
Let's look at the third. Let's look at the third line. See what would cause that. So we got this one. We got this one. What about this one?
It's not.
Any ideas?
X prime, Y, Z prime.
X complement. Y is okay. Z complement, right? Check. What about this guy?
That was.
We're okay with that, right?
Yeah.
Okay. Check. What about this guy?
X, Y prime.
I think we got him, but no way. Yeah, just Y prime, right? Check. What about this guy? Do we have him?
Yeah.
The third one.
It's the second one. It's X prime, Y prime, Z.
No.
No. Oh no.
X, Y, Z prime.
So what you're saying is we need X, Y, Z's complement, right? Okay, what about the last one?
It's fine.
Actually, any of these would give us that last one, right? Yeah. Any of these would give us the last one. Okay.
Except for the first one, wouldn't it? Because we ended.
Yeah, except for the first one.
Okay, I got you.
Anything with a complement will give us that.
Okay.
Okay, good job. Excellent. Okay, here we have another one. So here we go. Let's take a look at this one, the first one. So let me just write down X, Y, Z. X, Y, Z. X, Y, Z. X, Y, Z. Okay, so what will give us this first one?
X, Y, Z.
You mean your
Yes, I sure can. So do you think complement X, complement Y, complement Z? Is that the only way you can get it?
Yeah.
Okay. What about this one?
It's fine with that regular XYZ.
Wouldn't this give you the same? Wouldn't that give you the same result?
Yeah.
That's the bill, right? Doesn't that work?
Why?
Because not x is 1, not y is 1, and not z is 0. So the result will still be 0. So that also fits the bill, right?
Then how are all three, if it's the same thing, how come it was 1? Because it basically, because it was 1, 1, oh, 1, 1, 1.
Got it?
So like that.
Okay. So that was that, right? We got it. All right. How about this one here?
It's the first one work again.
First one works again, right?
Yeah.
Okay. How about this?
X complement.
X complement, YZ. Is that right? Okay, how about this one?
The first one.
First one, okay. Doing good on that first one. A lot of mileage. How about this here? First one, is that okay?
Yep.
How about this? What do you think?
Why you not see?
X, Y, not Z. Okay. And the last one.
The first one.
First one. We don't even need that, do we? So you get it?
So what would be the Boolean expression for 18 and 19?
So this is going to be the sum of products. These are both the sum of products that represent that truth table.
So, oh, that's that result.
Yeah.
Okay. Cool.
And the product is and the sum is the 4. Okay? Now, we haven't done, which identities are we still missing? In the post, I can't even say it. Yeah, and distributed. We'll cover that for sure on Monday. And we're going to flip-flop some Wednesday. We're going to okay, I was going to do Carnot maps today. We're not going to do them probably even until the week after. Okay, so here's what we're going to do and what we're going to cover. Just to let you know, because I know, like I talked to Saddam, he's like, what the heck? Explain half of this stuff. So, okay, today is a review of everything that I probably didn't explain it very well, so I'm doing a better job today. Monday, we're going to do a lot more identities and reduction. We're going to go back to flip-flops on Monday. And then Wednesday, we'll hit Carnot maps. Let's see, your assignment is due on Thursday. And the reason I pushed it out to Thursday is because I figured I needed to cover this stuff a lot better. Okay. Now, you know when your next test is, right?
Yeah.
October 20th. So what's on it? This exact stuff, mostly truth tables and circuits. Pardon me? Identities for sure. It should be pretty straightforward. And it's not going to be like the last test. You think the last test, the binary conversion, was just a little too much.
No.
No, you liked it. I just thought that was just too much grunt work. So this will be, I have more different things to give you, so I think your test will be a little more interesting. That's what I'm trying to tell you. Okay, so we're actually going to now do some more review on De Morgan's theorem.
This is the next part of simplification lecture where we're going to talk about De Morgan's theorem. And in the last section, we talked about simplifying equations when they only had single lines over single variables, like A naught or B naught or C naught. We didn't have lines over multiple variables. So in this section, we'll see how De Morgan's theorem works with lines over multiple variables. De Morgan's theorem says that large bars can be broken into smaller bars over individual variables. That way we can work with individual variables instead of things underneath them. We really can't do anything with them if the bar goes over multiple variables. So we have to break those up. So basically what happens with De Morgan is when you break a line, you change a sign. So you see in our examples here, I've got A and B and C with a line over top of the whole thing. Well, if I break this line right here, if I break this one where my arrow is, you can see it's going to be, it's and underneath that line. We'll break the line and the and becomes an or. And then the line now is just over A. Break this line and that and becomes an or, and we just have the line over B and then over C. So we break the line, change the sign. Break the line over ors, they become ands, and then the lines are split into 3 different pieces. So it's a way for us to get rid of these bigger bars and break them out into smaller ones. So we'll do some examples here. This is pretty much what I just showed you, but I wanted to show you a little bit bigger, a little bit where you can see a little better. Here's A and B not. So we've got AB with the not line over top of it. This, if we want to do De Morgan's theorem on that, you break the line right here, and then you change the sign underneath it. Since it's an and, we're going to change it to or. So we broke the line and changed it from an and to an or. So AB not is the same thing as A not or B not. Same thing with A or B not equals, break the line, change the sign, so or becomes and, A not and B not. So break the line, change the sign directly underneath where you broke the line at, nowhere else. So let's do this one together. And for this one, if you look, these lines are already broken. So the best thing I can do here is break the line right here. If I break the line right there, right underneath there is an and. So we're left with A not, B not, and then there's the line I broke right there. So I got the A not and the B not, and there's the line that I broke in half. Or becomes and. And remember, double inversions, if you have 2 things that are knotted, like A not not, it just becomes A. So that equals A, B. So that's the same as each other. They're equal to each other. If you look, yes, I could break this line, and then break this line, and then break this line. But if you look, if I break the line right here, it's going to create a line that's the same length as this one, and this line is going to be just covering those 2. So I would have 2 lines that were the same size, which means I can now cancel them out. So let's see what that looks like. I've got A not, and then that or becomes an and, B or C not, and then here's the line I broke, not. Lines the same length, the lines are the same length, I can just cancel those lines out. There's no reason to do anything else. So it's A, and then keep parentheses around things that have lines over top of them that you cancel. That way you keep them together. So you've got B or C. So A and B or C. You can multiply it through to see if it would go in simpler, but I don't think it will. We'll do it just to be sure. So you got AB, and then you got AC. No. So either one of those, you do either that or that. Either one of them are correct. I'll take either one of them. So try some of these. Break the lines up and see what happens. This one, you'll need to break it there and there. So make sure you change the line there. Make sure you change those. Make sure you.
Okay. First. A or B. This says not A. Okay, correct? Right, you forgot. Alright, so let's do this. Tell me what the first thing I need to do is.
Break the line.
Break the line and change the sign, right? So I have not. Did I do that right? Okay. Not cancels out. So I have A and not B. Correct? You good? Yeah. Ooh, we're going, okay, I'll just write it. A, B. Okay, so it's not A not B, A and not B. Okay, so what's the first thing I do? Break A or not B, right? Oh wait, we have knots on top of both of them. Did I do that right so far?
Yeah.
Now what? Not cancels out, right? Not A or B. Okay. This is a more complicated one, so we'll write it down. Not A plus C, not. Okay, what do you think we should do first here? Make a line here. So that leaves us with not A, and what's my sign going to be? Not B plus C, correct so far? Okay, now what? Cancel, is that right? So we're left with A, and we can actually drop the parentheses now if we need to, because it doesn't change the expression. Okay, we can write down the next one. A, B, C, Here we go. Okay, tell me what you think I should do first. Break that. A, B, and A, C. And I still owe some knots up top here, right? Okay. These cancel out. So is there any canceling on the left side I can do at this point?
Yes.
A.
Not yet, but I will,
A,
right? First I have to break the line. I'm gonna be able to. So this will be A plus B. That's a not, and that's a not, correct? We can suggest putting those in parentheses. Did we do that right so far? Okay. Not cancels. So we have A plus not B and AC. We could actually distribute that, but it would turn out to be more complicated, I believe. We'll just leave it like that. Just where to go. A, B plus C. Okay. So tell me what to do first. Oh, wait a minute.
There's more than one sign.
What do you think we should do?
Change both.
We can change both, or we can do it in pieces, either way. So if we break this, that becomes, for sure this is a not C, right?
Mm-hmm.
And the sign has changed. If we break this, this is not A, or not B, correct? Did I do that right? Yep. Okay. Ditch that, ditch that, ditch that, ditch that. That leaves us with A, or B, and C. Leave it at that. All right. Now, anyway.
Change the sign there, make sure you change the sign there. See how you do, and come back and we'll see the answers for it. Okay, here's the answers for them. And let me go ahead and show you how to work out some of these. If you break this line right here, you're left with A not, B not. And so the two lines cancel, you're left with A, B not. This one, break the line there, you've got A not or B not. Two lines cancel, you're left with A not or B. Here, we're going to break that line right there. It's A not or B or C not. Double lines cancel, so you're left with A or B or C. You drop the parentheses since they're all or together. This is the a little more complicated. You can break them one at a time though. So let's go, just break this one right here first. So we're left with, again, use parentheses to keep things kind of stuck together. A naught, B naught. And then this is going to be AC naught naught. And then we need to break this line. So we've got A naught naught or B naught AC, because two lines cancel each other out. And that actually equals that. Now we may be able to actually go even simpler. Let's do A times AC and AC times B. Let's see if we can go any further. So AC times A is AAC. And then we've got A, B naught C, right? AC, B naught, A, B naught C. The two A's go just to AC or A, B naught C. And we can pull an AC from both these, can't we? So you're left with 1 or B naught. All that cancels out, and you're left with AC. So it did simplify a little bit. For this one, let's break the line there, and we're left with A, B naught, naught, and with C naught, naught. So the two knots kind of go away, and the break the line there, and we're left with A naught or, because we changed the and to an or, B naught naught. Two lines cancel each other out, and we're left with C and A naught or B. And I multiplied through just to show you that it really didn't make it simpler. So hopefully that helps, and we'll move on to the next one. And if you need to pause it or go back, then do so. Now you may remember from algebra doing FOIL, first, outer, inner, last. All FOIL is a method of reminding you that you need to multiply certain things to each other so you won't forget anything. If you want to think about it, FOIL is just taking this one times both of these, and then taking the second one times both of these. Okay, so you got first, outer, well that's times both AB times AC, AB times BC. And inner is BC times AC, and last is BC times BC. So you're just taking AB times both and BC times both. That's all you're really doing. So let's work through this. And you've got AB and AC. We're going to take and do these two first. So if you do those two first, you've got AB, AC. I'm writing them down just like I would multiply them. And we do a plus. And then we're going to do BC and AC, AB and BC, the outer ones. And we're going to do the inner ones, AC, BC, or BC, AC. And we're going to do the last ones, BC, BC. Now if you go through and combine like terms, like A and A goes just to A, so you get rid of one of the A's. A, B, B, C is just A, B, C, because anything ended with itself is itself. A, B, C again, right here, get rid of the two C's and just put them in alphabetical order. And B and C just turns into B, C. So that's this line right here. Then from there, if you look, you've got a BC in every one of these. There's a BC in every one of those, so that's a like term. So if we pull out BC, we're left with A, or A, or A, or 1. Because you pull BC from BC, you got 1. All this stuff cancels out, and you're left with just BC. Give me a second to look that over, see what I did, and then I'll go on. Biggest thing is there's no squares in Boolean algebra, so there's no A squared or B squared like you would fill out normal algebra. Now this is the truth table, and I didn't ask you to fill it out because it's a really big truth table. But I did want to show you what it looks like. You'll notice here that I started with, we've got A, B's, and C's in here, so I just have a 3-variable truth table, which means I have 8 lines, 0 to 7, and I need the variable AB, I need an AC, and I need a BC. And then my simplified is actually BC. So I already had it here, but I like to put it at the end. So I did BC over here. And so we need to do our original. Our original, the first one we need to do is still the AB, the AC, and the BC. So we're going to AND these two columns, and these two columns, and then BC is ANDing these two columns. So that's how I got these. Then I'm going to do the first one. It's got AB or BC. Well, there's AB. There's BC. It's an OR, so I got a high there, and a high there, and a high there, because I've got two. Any high gives you a high, not both highs. Sorry. And then this one, AC or BC. So that's this one and this one. So ORing those, any high gives you a high. Out there's a high, and there's a high. And then the last one is to AND these two together. So right there. Two highs gives you a high out. So this one will be high, and this one will be high. So that's my original. And then the simplified one is going to be just BC. We already have it over here, so I just copied it over. And they're equal to each other, so that's great. We're done. That's all you need to do. So it's a little bigger truth tables. You may have some bigger truth tables, but they are equal to each other, so we know we simplify correctly. Last thing I want to mention is bubble pushing. And bubble pushing is another way to do De Morgan's theorem in pictures instead of doing it with the logic diagrams. I mean, the Boolean algebra, with the Boolean expressions, we can actually do it with logic gates. And the deal is that when you bubble push, you change the gate, which is the same thing as changing the sign, and any bubbles that are there, you take away, and the bubbles aren't there, you add them. So let's look at an example. So there's my original, and you can see I've got two AND gates and an OR gate. And I'm going to bubble push this last one. And for all the problems I'm going to give you, really all you have to ever do is bubble push this very last output gate, and it'll fix all the rest of them. So if we bubble push this gate becomes an AND gate, right? OR becomes an AND. And there were no bubbles on any of the inputs or outputs, so I'm going to add bubbles to all three, both inputs and the output. So these bubbles on the input could be just as easily back here as they can be up here. It doesn't matter which side of the wire I invert on, but this is not really a gate. But if I move these bubbles back, they say float the bubbles back on the wire, then you can see I've got three NAND gates. So I've basically taken it from an AND chip and an OR chip to a one single NAND chip. So I saved the company probably 20 cents per circuit just by doing that bubble pushing right there. Each chip is about 20 cents. So instead of having two separate chips, now I only have one chip. So an example with the AND gate. And again, take this AND gate, bubble push it, so AND becomes OR. There were no bubbles, so add bubbles. Float these bubbles back to there, now we've got all NOR gates. Again, save another 20 cents. But if you're making 1 million boards, that 20 cents adds up quite a bit. Try this one on your own, and pause it right here, and then I'll go on to show you the answer when you're ready.
Okay, so at the end is an OR gate, correct? Fed by an OR gate and an AND gate. I'm going to write what these are. And, OR. Okay. Oh, second crap. This is an OR gate. OR. And okay, so to bubble this, what are we going to do? There are two things we did, right? We change the bubbles, flip flop the bubbles, and we go from, this will go from OR to what? And then we change the bubbles. How do we change the bubbles? This is a bubble, which is a knot, right? So you take that away, Now back here, what do we do? Bubbles there. Okay, now we're not going to leave them there. So what did he do? He had that term floating, right? Can you see this? So we're going to put those there. This is a freaking mess.
Okay, this is the answer. And let me just show you how I did this. If you take this last one, but remember we're not going to do anything to the input ones because I said just do the last one. So those are not changing. But what's going to change is our last gate. So this OR gate is becoming an AND gate. We had a bubble there, so take the output bubble away. And we didn't have bubbles there, so add bubbles to the inputs, just like that. These bubbles float back, and then you're left with a NOR, a NAND, and an AND. Now, does it make sense to bubble push this one? Maybe not. You know, it may not make sense to actually bubble push this one. Maybe it would be this way. But there are cases where you need to bubble push. This was just a good example of kind of manipulating all of them together. Okay, practice these. Pause the video. Come back when you're ready.
Yes, sir. Let me just write them all down. Oh, no, I don't have to do them. Just remember. Okay. First, we change this to and we have to flip all our bubbles, right? Okay, now flip, bubbles cancel out. So we're left with, okay. So what he was saying was, is it worth doing this without have saved you any money? Remember those first two examples he gave you? He was able to have all NAND or all OR chips, all OR gates, meaning you can put it all on a single chip, so it saves you money. This is actually going from 2 NORs and an OR to 2 ORs and an AND, right? So it's not really end up saving any money probably, but by the exercise. So we have 2 NAND and an OR. So we flip that right. What do we do with rolls? That one goes. Keep that. And then AND gate. OR gate. So now how do we deal with these? They both float back, but these cancel, correct? So more. I get no words for that, do I?
That would actually cost us money, right?
Pardon me?
That would actually cost us money.
That would actually cost more, wouldn't it?
I mean, I know it's not part, it's an exercise we're going to
Yeah, but it definitely would cost more because you're going from two nands and an or to an and, or, and nor. So, yeah, question. Okay, cool. So, but these are really good to practice on for sure.
And again, bubble pushing, or becomes an and, flip the bubbles back to make them OR gate, or NOR gates. In this case, the bubbles actually cancel out. So, let me show you. So for that one, I've got an and with bubbles on all of them. And here I've got NOR gates with bubbles on the outputs. Well, what happens when you got two inversions? Two bubbles cancel each other out. Not and not just turn into just a regular line. There's no bubble at all there. So they cancel each other out. For here, the bubble floats back once you change it to an OR. And this one, the and becomes a NOR, and you float the bubbles back. Okay, you ready for the next section, which is called Carnot maps, and Carnot maps will be the last one in the simplification section.
We're going to do that next Wednesday. Let's kind of review some of our identities. I'm starting to run out of paper, unfortunately. So let's just do the really easy ones. 1x equals 1x equals 1.
Okay.
X. 0 and x equals 1 or x equals 1. 0 or x equals 0. Right? Right. I just want to read it before we go on to the next fun section. And I think we're going to run out of time for this, for sure. You guys, yes.
I'm sorry, quick question. So for the last one, you did 0 or x equals 0. I know we proved it earlier.
Oh, I'm sorry.
Okay, you know.
I'm sorry. We're going to run out of time on this, so I'm going to stop this. We're going to watch another simplification video, and at a certain point, I'm just going to stop it because we'll definitely be out of time.
We're going to start out this section of Boolean algebra and simplification with looking at all the different rules, laws, theorems, kind of go through examples of solving Boolean equations. So we're going to look at the basic operations, laws, theorems, Boolean algebra. We're going to use some truth tables to prove the Boolean theorems are true, that they actually did simplify correctly. And we need to be able to express our outputs for logic sort of using Boolean algebra. So Boolean algebra is really just a set of laws that are very similar to regular algebra. There are a few differences, but for the most part, it's very similar to algebra. You have your cumulative laws, associative laws, distributive, identity, and complement laws. So let's look at these. The commutative law, Boolean addition, means that you can basically add things in any order you want to. In other words, if we have the variables a or b, we can also say b or a. So we can rearrange those any way we want to. B or a or b. Same thing as in the example down here. I said 2 plus 6 equals 8, and so does 6 plus 2. It really doesn't matter what order you add them in. Same thing goes for multiplication. If it's a and b, it's the exact same thing as b and a. So 2 times 5 and 5 times 2 still equals 10, no matter which way you go with it. The associative law of Boolean addition means that we can basically group anything we want as long as it's all addition. So we can put parentheses around a or b, we can put parentheses around b or c, or we can get rid of the parentheses entirely and just have a or b or c. So really we can, as long as they're all OR, that's the biggest deal. You have to be all OR together or added together to be able to do that. Same thing with multiplication. We hang around the A, B, we can have parentheses around the B and C, or we can get rid of the parentheses entirely and just have A, B, C. So really, as long as they're all the same thing, you can do that. Distributive law, you may remember factoring in algebra. That's basically the same thing. In this case, we factor in, you multiply through the A. So A times B equals AB, and A times C equals AC. So you got AB or AC. In this case, this is a Boolean specific thing, which means A or BC equals A or B and A or C. There are no squares in Boolean algebra, so you wouldn't have, if you multiply these together, you wouldn't have an A squared, you would just end up with an A. That's how this one works. This one doesn't apply math, it's a logic thing only. Identity laws, very straightforward, and I can draw these out in the logic gates too, so you can kind of get an idea of what I mean. But the first one, A or 0 equals A. So let's say we have an OR gate, and you got A, and this one's always tied to +5, right? So any high gives you a high out. This one's always a 0, so if this was 0, this would be 0. If this is a 1, this would be a 1. So you can say that this just equals A. Same thing goes for, it's not on this page, but we'll hit it in a second, but it's a good time to show it. In an OR gate, if this one is always tied to +5, in other words, A or 1, anything ORed with a 1, remember, any high gives you a high out. If this one's always tied high, the answer always has to be 1. So A or 1, anything ORed with 1 equals 1. For the AND gates, it's kind of the opposite. If you AND, remember, it's anything, you have to have 2 highs to get a high out. So if this one's always high, if you get 0, 1, that equals 0. If you get 1 and 1, it equals 1. So basically the output follows A. If you AND that with 0 or ground and A, if this is always a logic 0, takes 2 highs to get a high out, the output always has to be 0. There's no way it could ever be 2 highs if one of them's always tied low, so it's always going to be a 0. And like I said, we'll see these two a little bit later on, but I wanted to show you those real quick. Anything ORed with its opposite is always 1. Think about it. Remember, OR gates, any high gives you a high out. Well, if these are complements of each other, if this is 0, that one has to be 1. If this one's 1, that one has to be 0. So one of them is always going to be high. So we know it always has to be a 1. AND gates is just the opposite. 2 highs gives the high out. Well, if they're opposite of each other, I'm never going to have them both being high if they're the opposite of each other or inverse of each other, so it has to be 0. So anything ORed with its opposite is a 1. Anything ANDed with its opposite is a 0. And think of it as just AND gates. Don't think about an OR gates. Don't think about it as necessarily math. Just think about it as gates. And any variable where I double invert it, like B not, if I invert it twice, it's just equals B. It's kind of like running it through, we've got B, and you got it going through one inverter, and then you got it going through another inverter. This would be B not, and this would be just B. Basically, you're taking away the line. So you just invert it twice, it just goes back to B. So it's a good thing to use when you're doing simplification. And why would you ever do that? Well, if you're solving an equation, you may very well end up with 2 lines over top of something, and you can get rid of the 2 lines. Dual property, and we kind of looked at this already in a couple of them, but the inverse of 0 is just 1, the inverse of 1 is 0. We know that. Anything ORed with a 1 is a 1. That's the one I was talking about a while ago. Anything ANDed with a 0 is 0. Remember, any high gives you a high out, well, that gives you a high out. You have to have 2 highs to get a high out. You can never have 2 highs if one of them is always 0, so it's a 0 out. Anything ORed with itself, anything ANDed with itself is just itself. And then anything ORed with its opposite is 1, anything ANDed with its opposite is 0. And these are all in your lecture notes too. So just to lay this out, let's say I want to simplify this one, and I'll show you in more detail later, but I'm not going to go through all of what the laws are that we use, but I do want to show you the step-by-steps later on. But in this case, we've got A or AB. if you kind of look at this thing, we've got two like terms. You've got A or A. What we can do is pull out an A. So what we need to do is write down the term that we're going to pull out, in this case an A, open parentheses. If you take an A from an A, it doesn't equal 0. It doesn't get rid of anything. It's left with a 1. So pull an A from an A, you're still left with a 1. And or, from the or, and you pull an A from an AB, and you're left with actually 1B. Okay? And then from there, anything ORed with a 1, remember anything ORed with a 1 is just a 1. So anything ORed with 1 is a 1. Anything ANDed with a 1 is just itself. So you end up getting an A. Now it seems really complicated and crazy and strange, but you'll get the hang of it. It may take a little while. This is probably one of the harder chapters you'll do, but you will get the hang of it, trust me. So why do we do this? Well, sometimes very complex logic circuits can be reduced without changing the function of the circuit. Think about if you had a circuit that had 25 logic gates in it, and you may want to reduce that down to maybe 5 gates. So if you can do that, then you can save the company quite a bit of money instead of paying for all these different chips. They're paying for a tenth of the amount of chips that they're using. Fewer gates means less money. The first step is always to write out the Boolean equation, and you have to have that laid out. Next step is apply rules, and then try to simplify it down whatever way you can. Try to remove parentheses and brackets, and try to find common terms, factoring in and out, and then construct a truth table to prove it. And we'll do some truth tables later on, but right at first we won't. But you usually want to provide truth tables to prove that your original and your simplifier are the exact same thing. And then you're going to draw a logic diagram of the reduced expression. Not the original, because it'll be too big. But if you do the simplified one, that'll be perfect. So let's look at this one. Let's work this one out. In this case, we've got AB and BC. And if you remember that law that said we didn't really, as long as they were all ANDed together, we really didn't need parentheses. So we can just write this out as A, B, B, C. We can drop the parentheses. Since it's all multiplied or all ANDed together, we can get rid of all the parentheses. Kind of like saying, we got AND gate, AND gate, AND gate. It's the same thing as saying 1, 4 input, AND gate. These are exactly the same as each other. So you've got A, B, B, C. Well, anything ANDed with itself, in this case the two B's, is just itself. So we actually end up with A, B, C. That's our simplifier. That's as far as we can go right there. To do the truth table, though, we want to do both versions. We want to do the original and the simplified. The original, don't try to do the middle one. Do it exactly like it is right there. Don't do anything different to it, okay? Just do the A, B, and A, B, C. Let me erase that for you. So I went ahead and did the truth table for ABC, and you can see it starts out, there's 3 variables, so 2 to the third equals 8. So there's 1, 2, 3, 4, 5, 6, 7, 8 lines. First thing we want to do is do the AB, right there. Then we're going to do a BC, and then we're going to AND these two together. So you've got AB and BC. That's the original. So you run up to, on the handouts or something that I give you, do an O, just to let me know which one the original is. And this will be the simplified one, is just A, B, and C. So A and B, we're going to AND these two columns together. So we're looking for 2 highs. 2 highs. BC is these two right here. And we're looking for 2 highs again there. And then we're going to AND these two columns together, A, B, and BC. And again, we're looking for 2 highs. And really the only time we have 2 highs is right there. So that's our original. All zeros with 1 at the bottom. A, B, and C means we're going to AND all 3 of these together. So basically, remember, all highs. So we're looking for 3 highs. And anytime we see a low, it's going to be a low out. So the only time we get one is right there. And are they the same? Yes, they should equal each other. If they don't equal each other, you've got a problem. So we simplified, we did our truth table, and now we need to draw our original, and we can, a
everybody got an extra 2 points on their test because of a mistake I made in the key. So you're all got a higher score.
See you Monday.